and it's a pleasure to introduce Zsolt Patakfalvi from Princeton, who will speak on the subadditivity of Kodaira dimensions with positive characteristics.
So thank you very much, Dan, for pronouncing my name. I would also like to thank the organizers for having me here, and for the audience for waking up this early. Subadditivity of Kodaira dimension is some problem in birational geometry involving Kodaira dimensions of bases and fibers and total space of the vibration. So first, let's talk a bit about Kodaira dimension, and for that, first about Kodaira Iitaka dimension. So unlike Kodaira dimension, Kodaira Iitaka dimension is associated to a line bundle. So unlike Kodaira dimension that's associated to a variety, Kodaira dimension is associated to a line bundle. So let's take a normal projective variety over a field. K is always a field. And let's take a Cartier divisor on it. And so then there are many definitions of Kodaira Iitaka dimensions. So let's just quickly sketch two of them. So first, one can define a Kodaira Iitaka dimension as so it's denoted by kappa of D, and it's negative infinity if no positive multiples of D have any section, any non-zero sections. Okay, and otherwise, one can define it as the dimension of the image of the rational map associated to some power of D, where this not power, some multiple, where this multiple is divisible enough. So of course it's not clear that this dimension is the same a priori for each divisible enough M, but this can be shown. So other definition that I would like to mention is that if you look at the growth rate of the space of sections of MD, then this will be asymptotically M to the power of Kodaira Iitaka dimension. Of course, in this situation, so maybe I write it out precisely. So it means that there are two real positive numbers, A, B, such that A times M to the Kodaira dimension, Kodaira Iitaka dimension is smaller than this dimension of the space of sections, and again, that's smaller than D times M to the Kodaira Iitaka dimension. And this is true only for divisible enough M. You cannot have it for all M's because there are examples where this space is empty for every M which is not divisible enough. So for M divisible. So these are the definitions. And having said the definition, let's look at some basic examples. So probably everyone knows that if D is ample, then the Kodaira Iitaka dimension. So you get an embedding as the map induced by D for some high power. So the Kodaira Iitaka dimension is maximal, is equal to the dimension of X. So another trivial example, if you have just the zero divisor, then of course again, your map is just contraction to a point, so the Kodaira Iitaka dimension is just zero. Some more interesting example, maybe still one easy one, when minus D is effective, Then it follows that, of course, all powers of D are effective. All powers of minus D are effective, so all powers of D have no sections to the Kodaira dimension. It's negative. Iitaka dimension is negative infinity. Unless D is 0, so yes, yeah, D is not 0. And, what? Non-torsion, yeah, non-torsion. Yes, effective is enough, yeah, non-zero is enough, yeah, okay. So, and then, let's soup up the first example. So, of course, you could say like, and just some multiple of D is ample, or rather, it's ample plus effective. So in this is by definition what we call big. So by definition, one of the many equivalent definitions of defining big. And this turns out, so then it easily follows that the Kodaira Iitaka dimension is maximal, maybe by the second example, second definition. But it turns out that this is equivalent to saying that the Kodaira Iitaka dimension is maximal. And so I didn't give example where you have intermediate Kodaira Iitaka dimensions, so between 0 and maximal. So the easy examples are products. So let's say X is Y cross Z, and you just take some ample divisor on Y, and you just define D to be the pullback of E. And then the Kodaira Iitaka dimension of D will be just the dimension of Y, which is intermediate if you chose a non-trivial product, so it's between dimension X and 0. Okay? So maybe these are examples, and so we introduced all these to define Kodaira dimension. So we need, it's an invariant of a variety, and so you want to use Kodaira Iitaka dimension to define something associated to a variety. That means you have to plug in, let's say X is smooth and projective. So you have to plug in a Cartier divisor that exists on every smooth and projective variety, which is the canonical bundle. Or canonical divisor, so the Kodaira dimension of X is by definition just the Kodaira Iitaka dimension of the canonical bundle. So just as a reminder, canonical divisor is the divisor associated to the highest wedge power of the potential in a smooth case. So again, easy example. So you have a, let's say Pn, and you have a smooth hypersurface of degree D in it. Then so we know from Hartshorne that in this situation the canonical divisor is just D minus n minus 1 times the hyperplane section. So in particular from the previous examples, then we can easily figure out what the Kodaira dimension is. So it's either negative infinity 0 or maximum, depending whether D is smaller, equal, or greater than n plus 1. Okay? So this is a standard example of Kodaira dimension. And so why do we like Kodaira dimension? We like it because it's a birational invariant. So remark, or I can call it a proposition, it's quite easy to prove it. So the Kodaira dimension of X is birational invariant of smooth projective varieties. And now one could think about how to extend this to singular varieties, because smooth varieties might be boring sometimes. You want to entertain yourself. So let's see. an example. So P2, and let's take a quartic curve in it with 3 nodes. Then this will be, in particular, something called a rational curve. So it will be birational to P1. So now, but let's compute the Kodaira Iitaka dimension of the canonical. Let's say this is X, this curve. So the same formula holds for the canonical divisor in this situation. It will be just 4 minus 2 minus 1 times h. So that's just h. So in particular, we're talking about the Kodaira Iitaka dimension of an ample divisor which is maximal, which is 1 in this situation. We're talking about the one-dimensional variety. On the other hand, if you look at the Kodaira dimension of P1, you know that the canonical is O minus 2. And you know that this is negative infinity. So we were screwing up our nice property that the Kodaira dimension is birational invariant if we were defining the Kodaira dimension of a singular variety with the same formula. So let's cross it out. It's not good. So instead, what one does, one can do different things. So if you're in a lucky situation when, so let's say we have a singular projective variety. And so if you're in a lucky situation when you have a resolution of singularities, then you can just define the Kodaira dimension to be the Kodaira dimension of a resolution of singularities. Okay? So this is plain and easy, and you see that this will be a birational invariant, of course, because we just sort of circumvented life. And but in positive characteristic, what this talk is about, we don't know this existence for dimension greater than 3. So, and we don't even know it for like big enough primes. So we really don't know it. So this means that you cannot do this. And instead there's a definition by Luo. So let me just say there is a definition. And it's by Luo in the article called Kodaira dimension of algebraic function fields. But the definition itself would take probably the rest of the lectures, yeah?
There's more than one Luo.
Yeah. So this is the brother of the Luo we all know. Isn't he? Okay, so okay.
But just a minute. I mean, so you are not answering. I mean, in your example, we need normalization.
Yes, even with normals you can do. So an easy example would be
No. I mean, what would be your definition of that situation?
I mean, normalization, I assumed part of the resolution of singularities. It's a birational map from a smooth. Okay, any other questions? Okay, so there is a definition, and I don't want to tell you what it actually is because it will take the rest of the lecture, but instead of that, let me tell you only one consequence, which is the only thing that's important for this talk, is that as there, you've seen that the Kodaira Iitaka dimension, the canonical was bigger than the Kodaira dimension of the variety actually, so this thing holds always, with using Luo's definition. So the Kodaira dimension of X is at most as big as the Kodaira Iitaka dimension. Okay, so this much introduction about Kodaira and Kodaira Iitaka dimensions. let's now go towards subadditivity, and let's think about how Kodaira dimension behaves. When you have some structure of your variety, so probably the easiest structure one can imagine is a product. So now everything is smooth and projective. So then from Hartshore we know that the canonical divisor will be the pullbacks of the respective, or the sum of the pullbacks of the respective canonical divisors. And in particular, if you apply Kunet formula to this, this is by Kunet, the sections of n times kx is sections of n times ky times sections of n times kz. You know that this is asymptotic to m to the Kodaira of y. This is asymptotic to m to the Kodaira of z. And this is asymptotic to m to the Kodaira of x. From where you just compare powers and you see that we have some additivity of Kodaira dimension for products. So Kodaira dimension of x equals Kodaira dimension of y plus Kodaira dimension of z. Okay. So what's more difficult than a product? A fibration. So let's look at an actual fibration example. K3, analytic K3. So you have a P1 base, a K3 surface, and the geometric general fiber is an elliptic curve. So if you write out the respective Kodaira dimensions, then we already see that the base has negative infinity Kodaira dimension, and both the geometric general fiber and the total space has trivial canonical bundle. So in particular, the Kodaira dimensions are 0. So you see that if you add them up, you get negative infinity, so there's no equality. So maybe I could end here the talk, but I don't. So Iitaka was brave enough to say that, okay, maybe there's not inequality, but maybe there's an inequality. Of course, based on many more examples. I mean, you cannot conjecture such a thing by using a function. And so just because later I will use this setup, let me be precise this time about the setup. So we have a fibration by which we mean the following. So x and y are smooth and projective over k. And we have connected fibers, which is equivalent in characteristic 0 to this condition. And let's keep it that way, because somehow we can eliminate some horrible things in positive characteristic. And so this is what we have, and then Iitaka conjectured that there's an inequality that k Kodaira dimension of the total space is at least as big as Kodaira dimension of the base plus Kodaira dimension of the geometric general fiber. So this was a major conjecture from around 75, and until now there's been a lot of characteristic 0 results. So one thing common about the characteristic 0 results that they use either Hodge theory or Kodaira vanishing. So in particular they fail or they don't fail, but their tools fail in positive characteristic. So they are not valid in positive characteristic. Still, let me just mention the names some of the names who were involved in this, in the characteristic 0 results. Maybe Ueno was an early person involved, then Kawamata, Tibek, Kolar, Chen Haken, Fujino and Birka. So, instead of saying all the results, it would take a lot of time. Let me just say one example result, and you can look them up all if you're interested in history. So, example result due to Kawamata. It says that, let me call star the conjecture itself, and it says that it holds if the geometric general fiber has a good minimal model, which means that it has a minimal model and that satisfies abundance. So some power of the canonical of the minimal model is base point 3. Okay. So this is the characteristic zeros for it, shortly. And so in positive characteristic, there weren't results until recently. So let me say something about that. So I proved something 2 years ago which was slightly restrictive or very restrictive based on how courteous you are. So I assumed F to be flat and the relative canonical to be relatively semi-ample. So instead of, it just means that some power is base point 3, but what's important that this is conjecturally given by the output of the MMT. And then I also have to assume this, that all fibers have mild singularities. For the experts, let me say that this mild singularities means F pure. And let me draw attention that this F is not the other F's. This is Frobenius.
This is the analog of
log canonical. This is the analog of log canonical for Frobenius sections. Okay? Okay, and what else? So this.
But I mean, you cannot throw away the bit.
No, unfortunately, with the methods I used, I couldn't. Probably there was some way. I never ended up working it out. My article, okay. This wasn't the main purpose of the article, so okay, so what else? I had to assume that we have maximum Kodaira Iitakas of the base and of the geometric general. So if these are maximal, it means that they are dimension 1 and dimension f respectively. You add up the dimension of the base and of the geometric general fiber, then you just get the dimension of x. So in this situation, this inequality tells you that actually this is also maximal, which means just that the Kodaira Iitaka dimension of the canonical is maximal, so it's big. The canonical of X. So that's what I proved. So anyway, let me just start in this situation. Right? So this was a bit like 2 years ago. Sorry? No, I didn't say y has dimension. It has any dimensions. Okay, and another result recently was by 2 Chinese mathematicians, Chen and Zhang. And they showed that if the dimension of the geometric general fiber is 1, then we're fine. So basically, they there's always some positivity results involved in proving this, and they use so what's special about the relative dimension 1 that you can use moduli of curves to get those positivity results.
Wait, is the general fiber assumed? Oh, this is the geometric general.
Yeah, one thing I forgot, the general side fiber is, so F is separable. So it implies that the geometric general fiber is integral.
Is the geometric general fiber normal?
It's integral, it's not normal, it's just integral.
So they don't assume normal, so where's the normal space?
They used a lot of this De Jong machinery somehow, so I didn't recalculate the article, sorry. But, I mean, that's what they used. That's what they used. Okay. Oh, yeah, I guess you can do a normalization in the beginning and somehow think this is I'll explain in a second. I guess there's something like that. So, yes, something like that, and you can replace it by, actually you can, in this case probably, yeah.
So, what are you seeing about
smooth and projected. Yes. And also I assume this condition, which implies that ky is algebraically closed in kx. It's integral. It's not smooth. It could be. So there are these quasi-elliptic surfaces that for which all this is true, and they have cuspidal. Okay. So these were the previous results. What I would like to mention here is the following result. So maybe I put it out somewhere, whatever. Maybe I will write it on some other board, because maybe I keep the conjecture and that up. So in the above situation, you have to assume two things. First, the base has maximal Kodaira dimension, so it's equal to the dimension. And there's one more thing, that the Hasse-Witt matrix of the geometric general fiber is not nilpotent. Meaning that it includes being non-zero. I will explain what this Hasse-Witt matrix is in a second. Just let me note that by saying my conjectures, theorems, and examples, this is some genericity assumption. So in this situation, we have the subadditivity statement. Okay? And so actually, so x and y are smooth. So this is just the Kodaira Iitaka dimension of the canonical. And you remember that I told you this proposition that this is always at the Kodaira dimension of the geometric general fiber is always as big as the Kodaira dimension. Kodaira Iitaka dimension of the canonical of the fiber. So in particular, if I had some inequality like this, that would imply the above inequality. And so this is what I actually proved. So really this Kodaira dimension wording is there just for historical reasons. Okay. So after the result, let's go. Let me explain a little bit what this Hasse-Witt matrix condition is and what. Not much easier, so that's not really the main problem. The main problem is
I'm wondering if this kind of condition that we put on the generic kind of a technical condition. So, if you look for
they are. So the main point is how do you circumvent Kodaira dimensions such Hodge theories. So somehow it seems that In practice, whenever you can circumvent it for a smooth vibration, usually you can just push it further to this situation. So really I could say smooth or normal general fiber. That's not the main point here. Okay. So let me talk a little bit about this Hasse-Witt condition, and let me say what the Hasse-Witt matrix is. So it's actually something very easy, to be honest. So you have let's say a variety over a field that has positive characteristic, and it's perfect. So perfect is just needed so that everything has a piece root, which is equivalent to being perfect, so it wasn't much. Okay, so if you have a variety like that, you can define the absolute Frobenius. So again, this F is not the geometric general fiber, it's the absolute Frobenius here. It's a morphism. It's really easy on points. It just takes every point to itself. So in characteristic 0, this would mean that it's the identity, but not in positive characteristic, where you can take a element, a function in the structure sheet, and you can send it to the piece power. And that defines, so that's compatible with all the charts, so it defines a morphism of, homomorphism of sheaves, and defines a morphism again. Okay, so this gives you, so this is a finite morphism in particular in this situation. And as to every morphism, you have the associated structure homomorphism, and you can apply that set, n to be the dimension of Z. You can apply highest cohomology to this homomorphism. You get what you get. And you can actually, so since F is finite, you can, this is the second thing is isomorphic again to just the top cohomology of the structure sheet. So this map is what we call the Hasse-Witt matrix. So that's a pretty easy notion actually. Pretty easily definable. Notion, of course, you could ask why is it a matrix, why isn't it a map? There's no canonical choice of basis, and you're right, there's no. So I have no idea what it's called matrix, but I keep it for historical reasons. Okay? Oh, yeah, you can compute, and that's the next thing I would like to say. So what are the usual examples of this? So if Z is an elliptic curve, that's so then of course n is 1, the dimension, so you're talking about H1 of the structure sheet, which we all know has dimension 1. So in this situation you have a 1 by 1 matrix. And so a 1 by 1 matrix is either 0 or non-zero. So there are two cases, whether an elliptic curve is ordinary or supersingular. And in the first case, the Hasse-Witt matrix is a non-zero 1 by 1 matrix. The second case is the 0 1 by 1 matrix. Second example, you look at the quintic Fermat hypersurface in P3. So this is your X. And so in this situation, you can compute very explicitly because you're talking about the hypersurface. and I did compute it. And what I got is that if 5 doesn't defy the characteristic -1, okay, first of all, what is this matrix? This is a 4x4 matrix, because you have H1 of OX is 4-dimensional, you can compute that. And so again, if P-1 is not divisible by 5, then you get the complete 0 4x4 matrix. If P is divisible, P-1 is divisible by 5, then you get some non-zero number times the identity 4x4 matrix. Okay? Any questions? So, these two examples show you sort of in what sense is the non-nilpotency of Hasse-Witt a genericity condition. So there's two ways you can word this, and I will say most of these things in words. So the first example tells you that when you fix the characteristic and you vary your variety in moduli, then most of the elliptic curves are ordinary. So most of the Hasse-Witt matrices should be non-nilpotent. And so this was conjectured in this vague sense by Grothendieck, I think. And it was proven in quite a lot of cases. So Nick Katz has a theorem saying that every high enough degree general hypersurface section of Cohen-Macaulay equidimensional scheme has non-nilpotent Hasse-Witt matrix.
This is fixing P.
Fixing what?
And this is fix P, and then it's either.
Yes. So this is where you fix P. No. But it's projective. No, you take high enough degree hyper surface. So I think for high enough degree you're fine. You don't need any. I mean, you can read it. It's in AGA7 too. SGA, sorry. Borgov corrected me. Okay. There's no EGA7. So that's one thing. You have, and then also in most cases we know that for general variety the Hasse-Witt is not nilpotent. So for case trees, you know that most case trees have non-zero Hasse-Witt or non-nilpotent Hasse-Witt for abelian varieties. So whenever we have a concrete moduli, usually it's known, and it's no one's theorem because usually it's easy to do. The second example shows you a different genericity behavior. So when you vary the characteristic, and you fix first the characteristic 0 variety, and you reduce it mod P, and you vary the reduction, then it's expected that for infinitely many primes, the Hasse-Witt will be actually bijective. And so this is a conjecture written down by Mustatse and Srinivas. And what's surprising is that it's not known, even for like genus 3 curves. So it's known for elliptic curves and for abelian surfaces, which implies genus 2 curves. And then, as far as my understanding goes, this is where the theory starts. So I think it's a nice curve actually. Maybe it's doable in the genus 3. Oh yeah, thank you. So having said this, there are other questions. Let me say something about the proof. So ideas from the proof. So you want to prove, let me assume that the geometric general fiber is big. It has big canonical, equivalent to the Kodaira dimension of that canonical is the maximum. So what do we want to prove? So as I said, already, but maybe let me, just for safety. So I want to prove this, this lower version of the inequality. This is what we want to prove. And so we assumed there's this first assumption in the theorem, and now I made the second assumption that everything is maximal. So in this situation, of course, this sum comes up to just dimension of x. So saying that the Kodaira Iitaka dimension of the canonical is at least dimension of x is the same as, so what we really want is that it's big. Okay. I didn't reduce, I'm just looking at this special case here. Okay? Just to make it easy. Okay. Yep. Oh yeah. Thank you. This is that. Thank you. So this is what we want, and so let's have some initial considerations. So under this assumption that the canonical of the geometric general fiber is big, one can prove that this is the relative canonical is relatively big, which means that it can be written, it's a Q equivalent to something relative ample plus effective. So if you have a relative ample, then you might remember that if you add some big pullback of a big ample from the base to it, then it becomes actually ample. So in particular, so if you look at the relative canonical plus some big multiples, so you should think about P being huge, as big as you can think. So T times the pullback of an ample from Y. Then what do you get? So this is Q equivalent to A plus T times the pullback of H plus E. And so as I mentioned, for big T, this will be ample. So you have ample plus effective. So if you remember, that was our definition of big. So in particular, this divisor, the relative canonical plus T times the pullback of H is big for T big enough. Okay, so let's see what can we work out of this. So we want to show that Kx itself is big. So we're sort of, we're almost there. We just have to get rid of this guy here and somehow put in the canonical of Y. So let's sort of try to write Kx in a smart way. So you can write it relative canonical plus the pullback of the canonical of the base. And then, you know that there's this term that we already understand because it's big. And now let's see what we have if we put epsilon times this in the picture. So then to get equality, what do you have to still add to this equation? You have to add 1 minus epsilon times the relative canonical. So then we have at least equalities on the level of the relative canonical, but I add some epsilon times pullback of H also to that for the flavor, and then now I really don't have equality on the level of the pullback of Ky, and there's a lot of pullbacks of H's in the picture, so I just add all the terms that are missing to the end. So what do we get? We get pullback Ky minus epsilon times t plus 1 minus epsilon times h. Okay, I hope you survived this equation.
Is that an equality between the x directly line?
Sorry?
The equality goes to the other line.
Yeah, so the equality, so there it continues. So this whole big expression is equal to kx. Okay? I mean, if you don't, yeah, it is. And so the important thing to see here that this last term goes to 0. This guy goes to 0 as epsilon goes to 0. So epsilon, of course, always goes to 0. Epsilon. Okay. So so in particular, you have a ky is big. So this whole pullback will be effective for small enough epsilon.
But couldn't you take instead of h?
Yeah, you could maybe. Not for there will be other parts. So this h will be used later in the talk, or later, I mean a few minutes later. Yeah. So at this point I could use that. I just will have this h on with me. Okay. So this guy in the end is so this last term. Unfortunately, I wrote it to the bottom of the board, so a bit hard to denote. But this last term is q equivalent to an effective because of this convergence to 0. And then you know that this guy is actually big. Okay, so in particular, if we could prove that this thing is also q equivalent to an effective, then we would be ready. Because we would have effective plus big is big. So that's the next step. That's what we're really going for. So this is sort of pseudo-effectivity like statement. So this is what we really want. That the relative canonical plus some little epsilon times the pullback of h is q equivalent to some effective. So it's a slightly stronger than pseudo-effectivity because the pullback of h is not ample. So we require this for every epsilon small enough. Epsilon is rational. So it's like pseudo-effectivity. If this was ample, then this would be actually saying that kx over y is pseudo-effective, but this is slightly stronger. Okay, so the way we do it is just continuity method. So we know the statement if epsilon is big, because what we had here, that it's actually big. If this divisor if epsilon is big, so then decrease epsilon gradually, so that it goes to 0. So what does this mean? So that you have some section of some multiple of divisor is actually linearly equivalent, not just q equivalent to a divisor. So let me write out what this means. So you have, what this means that you have some multiple, let's say a times the relative canonical plus b times the pullback of h, which is actually honestly linearly equivalent to an effective divisor. And you want to produce another divisor with some different coefficients that is also linearly equivalent to a divisor, such that the limit of this, so if you repeat this process, the ratio of these coefficients goes to 0. So I'm not going to be able to show you here this entire argument, because it involves passing to a Frobenius pullback of the base, so the pulling back the entire vibration. But I will be able to show you a main step, which involves like the main tools used recently a lot in positive characteristics, which shows you how to find a section of A plus 1 relative canonical plus b plus 2 fullback of h. So this will be the implication. So how to find the effective divisor? We actually equivalent to this one. Given that h minus ky minus dimension of y times a is, oh, this is a different a than before, is variable, because this a lives on y, and we want it to also be variable. Okay? So with these conditions, this is the step that I would like to talk about, and the goal is to sort of present these new ideas floating around in positive characteristic recently. So let's go to another board, maybe here. So the main tool is something called the Cartier module. It is, in certain sense,
over A that you want.
Yes, so that's what I'm saying, that we need a Frobenius pullback in the argument that
B over A you want to 0 and
that's what I'm saying, that we need this Frobenius pullback. So you need to apply this on a Frobenius pullback, and then H, the Frobenius pullback becomes H over P to the E. And this is the main thing that we also exploit in the actual argument.
So then what doesn't do equality?
Sorry? So if you I was trying not to put this technicality in it, but you should pass everything to the Frobenius pullback. So you should pull back everything to the Frobenius pullback, and then you actually can put, in particular, you can move it back in the end, and this will be v plus 2 over P to the E roughly. And that's how you get this convergence to 0.
Why isn't this enough? Why do you need something more than
No, that's all I need. A Frobenius pullback.
But why not on the first line?
It's called Frobenius pullback plus 3 the ratio, right? Like you can't.
Yeah, let me explain what I have.
So start with A plus B plus 1. Then you're making the life worse.
No, I'm not.
You are. Then everything went C, so that's worse.
But, whatever. Let me present this stuff.
You didn't mean pullback, which you need A and B.
So A doesn't change, B changes. B goes to P over B over P to the E. You use another H, so the point is, okay, I can talk about then the Frobenius. This is what first one. So, if you pull back H by a Frobenius pullback, then it becomes P to the n H. So I don't know if you know this usual trick in positive characteristics. So in particular, this thing here gets replaced by yes, this gets replaced by. So what you're going to have is A kx over y plus P to the n B H will have a section. Okay? But of course, it seems like you made your life worse. But, so the point is that if you apply this step here, then you have much little change on in the second coefficient. So you will have, so when you move back to the original guy, then really the change will be 2 over P to the n. Okay? So really you can roughly say by Frobenius fullback you can modify this process so that you put a 2 over p to the n here. Okay? Does this explain what I'm doing?
Okay, so your argument will prove that b is less than or equal to 2 times a.
Yeah, something like that.
Then you run.
Yes.
It's 8 then.
Exactly. Okay? So, I hope this explains what's going on. So, but let me tell you the main. Okay, I really wanted to talk about Cartier module, sorry, so maybe I should have talked about this Frobenius part, but let me tell you what the Cartier module is. Because so as I told you, Kodaira vanishing is the main thing that fails. And this is, so if you read Kodaira vanishing proofs, or you sort of, read it, then it's proven with Hodge theory, or with the added Hodge theory. In either way, it sort of uses some D modules. And there's this notion of Cartier module that is closely related to D modules in positive characteristic, and it seems to be the correct replacement of all the Hodge theory machinery. So, on the other hand, it's a very surprising, easily definable notion. So this is a Cartier module. If M is just a coherent sheet, and phi is a ordinary morphism from the Frobenius push forward of M to N. It's a pretty easy notion, that's it, there's no more. But, so let me say, let me give examples of this. So as I told you, Frobenius is finite in this situation that I'm working in. So in particular, you might remember from Hartshorne that there's a trace morphism associated to every finite morphism like this. So this is the trace morphism introduced in Hartshorne chapter 3, section 7, I guess. So it is a Cartier module, you see. So how can you cook up other Cartier modules? How can you cook up other Cartier modules? So we have that gamma in our setup, and you can twist omega x with gamma. And now what you can do, you can embed this into omega x twisted with p to the e gamma. So this is just the usual embedding, what's natural. You multiply with p to the e sorry, there's no e. P gamma. And now you use the weird tricks of positive characteristic that I already mentioned, that p times gamma is just the pullback of gamma by the Frobenius. So maybe I write it just here. This is the pullback of gamma. And now using projection formula, so this is projection formula, you get that this is just nothing else but the push forward of omega x twisted with gamma outside. So what you can do, you can apply this trace that we have up here, twisted with gamma, to this shift, and you will land in omega x twisted with gamma. If you do this composition, you get a Cartier module that let me denote by trace gamma. Okay? So, but actually I need a Cartier module on y. So how can you, if you have a D module on x, how do you do a D module on y? Well, you just push it forward. So the same thing works with Cartier modules. So this is the third example of Cartier module. You take that thing that we have there, and you push it forward. By up. Okay? So now this this looks like not a Cartier module, because F is not on the outside. So, but there's this magic trick that Frobenius commutes with everything, and you can exchange these. And then this is a Cartier module, let's call it the morphism, push forward of trace gamma, and the sheaf itself and gamma. Okay, and so what's our goal? So I will say just the rest in words because I ran out of time. So we want to find the section of this guy. So that's very similar to finding a section of that one, because section of push forward is the same as the section of the original. So now, how can we find the section of that one? So it turns out that there's a theorem, maybe I write just this one up, by Keeler, that this sheaf has this Cartier module, M gamma, has something called the stable part, for which, if you twist that with OH, then it's globally generated. The proof uses Mumford's global generation criterion, using Mumford Castelnuovo regularity. And so this is the main tool we're using with this Cartier module. This way I get a section of omega x twisted with gamma, and then you can see that that is almost this this sheaf. It's actually, the difference is effective. So then actually get a section of this divisor. Okay, so that's the rough outline of the end. I wanted to advertise Cartier modules and this neat global generation result used a lot. Thank you.
All right, questions to the speaker?
So I assume that the Hasse-Witt matrix exactly does the zero and non-zero.
Exactly, that's what we're using for. And I mean, of course, so there are many open. It's not equivalent, unfortunately. So it's kind of hard to do with Hasse-Witt matrices. That's one of the big problems we have in positive characteristic geometry. And of course, we would like to replace this with some kind of asymptotic motion, like maybe some S not Kodaira dimension, not zero, or at least zero. So yeah, we also don't have any counterexample. Unfortunately, even if we don't assume separable, so maybe the fibers are all have nilpotent structure, you feel there should be something, but we don't have any counterexamples. So I mean, if anyone finds one, it would be great. We don't have any counterexample, unfortunately.
But what kind of situation is open?
So by counterexample, I meant in ugly situations in positive characters. So in the ones I excluded. And in characteristic zero, the main open question is, so you remember Kawamata's result, that when the geometric general fiber has a good minimal model, then you're fine. So whenever this is not known. So for example, I think probably the hardest case should be where abundance should be hardest, which is Calabi-Yau manifolds. So the fiber is Calabi-Yau, so it's a family of Calabi-Yau. I don't know any example, but of course I'm looking at constantly.
What about cache? This seems to work if you have a pair that comes from the base.
Yes, the base should be fine to add. It's more tricky. So I've been trying to add pairs with the, but actually even in characteristic zero, I'm not sure. I don't really know one good example there aren't, let me say this, usually even in characteristic zero Kodaira dimension, Subadditivity is done so the fibers don't have pairs. But maybe there are some articles, there are pairs in characteristic zero, I don't know.
Thanks to the